So here's another homework problem. This is a non-uniform field. So we've done these uniform fields. A uniform field on a dipole in a uniform field won't have a net force, but it could have a net torque if it's not pointed in the right direction. Here is a non-uniform field. The problem specifically gives you the magnetic field. This J hat is supposed to be a unit vector in the y direction. K hat here is a unit vector in the z direction. You can see that x is to the right, y is up the screen. And so z is out of the screen. X, y, and z are a right angle system, and so z has to point out of the screen, sorry, a right-hand system as well as right angle. So z points out, y is up the screen, x is to the right. The magnetic field has a y component, because there's a j hat there, and it has a z component. And they vary with position. So you look at, there's a lot of stuff going on here. So let me just tell you basically the way I look at this. The y component, this component that's j hat, has b0. It's got L, but I don't care about L really. That's just a constant. B0 is a constant. So this y component varies with z. The part of the field that points up the screen depends on z, and at z equals 0, it's 0. So that's something you can look at quickly. By the way, you can calculate the forces just by this force vector has components. And so you can calculate and it depends on a cross product, and so you can calculate the components by putting in all the pieces whenever you want to. So you can do the math. But what I wanted you to do was do the thinking. The y component at z equals 0 is 0. The z component of the magnetic field, there's a component to the magnetic field that points out of the screen along z, and it's 0 at y equals 0, and gets bigger and bigger as you go to larger y, and negative as you go to negative y. So, given all of those things, what's the direction of the net force on this loop by that non-uniform field? Talk about it all you want. I'm going to give you a little extra time because there's so many things going on here. So you're running out of time. Really want to focus on what's important here. Curious to see what the answers are. All right, I was afraid of that. I mean, there's a lot of thinking involved here, and if you don't kind of go through it in the right way, you can get twisted up and messed up completely. So you have to go through it slowly and carefully. What I tried to do in telling you about the field was to tell you that the y component of the field is 0 at z equals 0. And this whole loop is at z equals 0, even though I didn't say that. So the y component of the field you can ignore completely. This loop does not feel a y component of the field because the y component goes to 0 at z equals 0. So you can forget about the y component of the fields. Then you just need to worry about the z component, the component of the field that comes out of the page, out of the screen, or into the screen. Now, it turns out it comes out of the screen because it's positive everywhere, or it's 0. Turns out it's 0 at y equals 0, so there's no field, magnetic field down here, out of or into the screen, or in any other direction, actually, right along this one. Along this one right here, the magnetic field, this is a positive value for y, so the magnetic field up here points out of the screen in the positive z direction. So what happens is the magnetic field points out of the screen and gets bigger and bigger and bigger as we go up in y. That's what that equation for the magnetic field is telling you. If you have a current upward, like the left-hand side of this loop has current in the y direction, the magnetic field is in the positive z direction. It's getting bigger and bigger as you go up the loop, as you integrate over y. And so that'll give you a force, and that'll give you a force that's what, to the right? Yeah, because the magnetic field's out of the page, so that'll give you a force to the right here. But that's going to be canceled by an equal and opposite force to the left over here, because this has the same current and the same set of magnetic fields. So those are just going to cancel each other. What isn't going to cancel is that there's no force down on the bottom because there's no force magnetic field at y equals 0. The z component of the magnetic field right here goes to 0 at y equals 0, so there's no force there. There is a force up here at the top. The z component of the magnetic field points out of the board. So there's a force down the screen, it looks like, on that one. And so that's the only force that isn't balanced by some other force. And so I think that actually was the main answer, slightly. Down the screen is what I hoped that you would come out with here. Any questions on that one? All of these things tend to, these get kind of complicated if you're not really good with a right-hand rule for one field and for one current. Once you get good at that, then you have to just either make notes about forces or draw pictures or kind of try to keep it all in your head. I would suggest drawing pictures just to remind yourself the directions of the forces. But of course, as I said, there's a mathematical way to calculate all the forces. And so you can just calculate all of them and add them up. And hopefully, you'll find out that it's in the negative y direction down the screen, the total force.